The North Atlantic, winter of 1941. The water was black as ink, churned by winds that had been howling for 3 days straight. Somewhere beneath those freezing waves, a German submarine was about to test a technology that would change naval warfare forever. But nobody knew it yet. In fact, most people who knew about this technology thought it was completely useless. This is the story of how a simple sheet of rubber, riddled with holes and initially dismissed as a failure, would become one of the most closely guarded secrets of submarine warfare. A story of persistence, scientific brilliance, and a race against time in the darkest days of the Second World War. Chapter 1. The Invisible Enemy. To understand why this rubber coating mattered so much, we need to go back to the beginning of the war. By 1939, submarines had become the weapon that kept admirals awake at night. These steel predators could strike from nowhere, send thousands of tons of shipping to the bottom, and vanish before anyone could react. The German U-boats were particularly terrifying. They hunted in groups, coordinating their attacks with ruthless efficiency. Between 1939 and 1945, they would destroy more than 5,000 Allied ships. That's not just numbers on a page. Each of those ships carried cargo vital to the war effort: food, fuel, weapons, ammunition. But more importantly, they carried people, sailors, soldiers, civilians. Over 15,000 lives were lost to submarine attacks in the Atlantic alone. The Allies were desperate for a solution. They had one powerful weapon in their arsenal, a technology that could detect submarines even when they were hiding beneath the waves. The British called it as-de-lao. The Americans would later call it sonar. Both names describe the same revolutionary principle, using sound waves to find submarines underwater. Here's how it worked. A ship would emit a pulse of sound, a ping that traveled through the water. When that sound wave hit something solid, like a submarine hull, it bounced back. By measuring the time it took for the echo to return, operators could determine exactly where the submarine was hiding. It was like using a flashlight in a dark room, except the flashlight was made of sound. ASDIC was devastatingly effective. Submarines that had once been invisible hunters suddenly found themselves becoming the hunted. The technology operated primarily in the 14 to 22 kilohertz range, a frequency that traveled well through seawater and reflected strongly off metal hulls. When a submarine was detected, escort ships could move in and drop depth charges, powerful explosives designed to rupture a submarine's hull through sheer pressure. The early results were promising. British and Allied anti-submarine forces began racking up victories. U-boat commanders who had once roamed the Atlantic with impunity now found themselves detected miles away from their targets. The balance of power was shifting, but the Germans weren't about to give up their underwater advantage without a fight. Chapter 2. The Acoustician. In the spring of 1939, a German scientist named Erich Meyer was working in his laboratory, studying the properties of sound. Meyer was what we call an acoustician, someone who specializes in understanding how sound waves behave. He was particularly interested in a phenomenon called acoustic absorption, the way certain materials could trap sound waves instead of reflecting them back. Meyer had been following the development of ASDIC with growing concern. As Germany's leading expert in acoustics, he understood better than most how vulnerable submarines were to this new detection technology. He also understood something else. If a material could be designed to absorb sonar waves instead of reflecting them, a submarine coated in that material would become nearly invisible to enemy detection. The concept wasn't entirely new. Scientists had long known that certain materials absorbed sound better than others. Concert halls used acoustic panels to improve sound quality. Recording studios used foam padding to eliminate echoes. But those were static installations designed to work in air. Making something that would work underwater, under immense pressure, while moving at speed, That was an entirely different challenge. Meyer began experimenting with synthetic rubber. The Germans had become quite skilled at producing synthetic materials, driven by necessity as wartime blockades cut them off from natural rubber supplies. Through the chemical giant IG Farben, they had developed a material called ulpanol, a specialized polyisobutylene polymer that remained flexible even in cold water. But Meyer's innovation wasn't just using rubber. It was what he did to the rubber that made it revolutionary. He created a material with thousands of tiny air voids, holes of specific sizes distributed throughout the rubber in a precise pattern. These voids weren't random. Each void was carefully calculated to trap and dissipate sound waves at specific frequencies. When a sonar pulse hit this perforated rubber, something remarkable happened. Instead of bouncing back as a strong echo, the sound wave entered the voids. Inside these tiny cavities, the sound wave's energy was converted into heat through friction and absorption. The echo that returned to the Allied ships was reduced by about 15% of its normal strength. 15% might not sound like much, but in submarine warfare, it meant the difference between detection at 3 miles or detection at half a mile. It meant the difference between having time to dive deep and evade or being caught on the surface. It meant the difference between life and ending up on the ocean floor. Meyer was excited. He had created something that could potentially save thousands of German sailors. The German Navy was intrigued. They gave the project a code name, Alberic, after the dwarf king from German mythology who possessed a cloak of invisibility. It seemed like the perfect code name for a technology that would make submarines invisible. But there was a problem, a big problem, one that would almost derail the entire project before it could prove its worth. Chapter 3, The Adhesive Problem, Spring 1940. The German submarine U-11, a small Type 2B coastal boat, sat in a shipyard on the Baltic coast. Engineers swarmed over her hull, carefully applying sheets of Meyer's rubber coating. It was painstaking work. The synthetic rubber came in panels about 1 meter wide and several meters long, each 4 millimeters thick. Every panel had to be precisely positioned and secured to the submarine's steel hull. The workers used a special adhesive, a glue developed specifically for bonding rubber to metal. They worked carefully, knowing that any gaps or bubbles could compromise the coating's effectiveness. It took days to complete the job, thousands of man-hours of meticulous labor. When they were finished, U-11 looked strange, covered from deck to keel in black rubber. But the real question was whether it would work. The initial tests were promising. In calm waters, with the submarine stationary, ASDIC operators reported significantly weaker echoes. Meyer's calculations had been correct. The perforated rubber was absorbing sonar waves just as he had predicted. The German Navy was impressed enough to order a full operational test. In April 1941, they selected U-67, a Type 9C ocean-going submarine, for the honor. This would be the real test. Not in calm Baltic waters, but in the harsh conditions of the North Atlantic, where U-67 was scheduled to begin war patrols. The coating was applied at the shipyard in Wilhelmshaven, covering not just the hull, but also the conning tower and bow. U-67 departed on her first patrol with great hopes. The crew had been briefed on their special coating. They understood they were testing technology that could change the course of the submarine war. They sailed west into the Atlantic, heading for the rich hunting grounds off the African coast. Then disaster struck, not from enemy action, but from the ocean itself. As U-67 moved through the water, crew members began noticing something alarming. The rubber coating was peeling off, large sheets of it loosening from the hull and trailing behind the submarine like grotesque ribbons. By the time U-67 reached her patrol area, an estimated 60% of the Alberic coating had been lost to the sea. The problem was immediately obvious. The adhesive wasn't strong enough. Under the constant pressure of moving water, the combination of temperature changes, the flexing of the hull, As the submarine dove and surfaced, and the simple mechanical stress of traveling through the ocean, the glue was failing catastrophically. But the nightmare didn't end there. The partially detached sheets of rubber flapping in the current created terrible noise. The edges caught water, creating turbulence and vibration. Instead of making the submarine quieter, the peeling coating made it louder. U-67 had become easier to detect, not harder. It was a humiliating failure. When U-67 returned to port, the decision was made quickly. Strip off what remained of the coating. More tests were conducted in the Little Belt Strait, trying to salvage something from the project, but the results were disappointing. By August 1941, all the alberic coating had been removed from U-67. Meyer's revolutionary idea seemed dead in the water. The German Navy had more pressing concerns. U-boats were needed on patrol, not sitting in shipyards while engineers experimented with coatings that didn't work. The resources required, the thousands of man-hours of application time, the shortage of synthetic rubber, all for a system that fell apart as soon as it got wet. It simply wasn't practical. The alberic project was shelved. Erich Meyer's useless rubber coating became a footnote, another failed wonder weapon that German scientists had promised would change the war but couldn't deliver. For 3 years, the project gathered dust. 3 crucial years during which the Battle of the Atlantic raged. 3 years during which thousands of sailors perished in the freezing waters. 3 years during which the outcome of the war hung in the balance. But Meyer hadn't given up. Neither had a small team of chemists at IG Farben. They knew the concept was sound. The problem wasn't the rubber coating itself. The problem was the glue. Chapter 4. The Solution. The year was 1944. The war had turned decisively against Germany. Allied forces had landed in France. Soviet armies were advancing from the east. The Luftwaffe was being swept from the skies. And in the Atlantic, U-boats were dying at an unprecedented rate. The Allies had perfected their anti-submarine tactics. New radar systems could detect a surfaced submarine from miles away, even in darkness or fog. Better sonar equipment could track submarines underwater with frightening accuracy. Hunter-killer groups, teams of destroyers and aircraft carriers dedicated solely to finding and destroying U-boats prowled the shipping lanes. By 1944, the life expectancy of a U-boat crew had become measured in weeks, not months. The German Navy was desperate for any advantage, any edge that might tip the balance, even slightly, back in their favor. It was in this atmosphere of desperation that someone remembered Erich Meyer's rubber coating. The adhesive team at IG Farben had continued their research throughout those 3 dormant years. They had been working on new polymer formulations, trying to create a glue that could withstand the brutal conditions of submarine operations. They believed they had finally cracked the problem. The new adhesive was chemically different from the original. It formed molecular bonds with both the steel hull and the synthetic rubber. It remained flexible in cold water, but didn't weaken. Most importantly, it maintained its grip under the mechanical stress of moving through water. At least that's what the laboratory tests suggested. But laboratory tests and real ocean conditions were 2 very different things. The Navy needed proof. They needed a submarine willing to test the new alberic coating under actual combat conditions. They chose U-480, a Type 7C submarine currently under construction at the Deutsche Werke shipyard in Kiel. U-480 was a standard workhorse submarine, 220 feet long, carrying 14 torpedoes, crewed by 48 men. There was nothing special about her design, but she was about to become the most important submarine in the German fleet. Beginning in the summer of 1943, right from her initial construction, U-480 received the alberic treatment. This time, the engineers were taking no chances. They applied the new adhesive exactly according to the improved specifications. The rubber panels were carefully positioned and pressed onto the hull. Then, As an extra precaution, they added rivets at key stress points. It took several thousand hours of labor. Men worked around the clock, applying and checking the coating. Every square meter of U-480's hull received this careful attention. The submarine was commissioned in October 1943 under the command of Oberleutnant Hans Joachim Förster, a capable and experienced officer. Förster was briefed on the experimental nature of his boat. He understood that U-480 was as much a test platform as a weapon of war, but he also understood something else. If the coating worked, if it could truly make his submarine harder to detect, it would give him and his crew a precious advantage in the deadly game of hunter and hunted that played out beneath the Atlantic waves. U-480 went through her sea trials in early 1944. The engineers watched anxiously as she dove and surfaced repeatedly, as she maneuvered at various speeds, as she endured the temperature changes and pressure variations of operational diving. And the coating held. Every inspection showed the rubber panels firmly attached with no significant peeling or detachment. The submarine was fitted with a snorkel breathing apparatus in May 1944, another recent innovation that allowed submarines to run their diesel engines while remaining submerged, drawing air through a snorkel tube. With both the Albrick coating and the Schnorchel, U-480 represented the cutting edge of German submarine technology. But the real test was yet to come. Theory was one thing. Combat was something else entirely. Chapter 5. Into the Channel, August 1944. The Allied invasion of France had succeeded. American, British, and Canadian forces were pushing inland from the Normandy beaches. The Germans were in retreat, but they weren't defeated yet, and they certainly weren't about to give up control of the English Channel without a fight. The Channel was the busiest waterway in the world. Allied convoys moved through it constantly, carrying supplies, reinforcements, and equipment to support the advancing armies. These convoys were vital to the Allied war effort, and they were vulnerable. The German Navy made a fateful decision. They would send U-480 into the English Channel. It was one of the most heavily defended stretches of water on Earth. Allied anti-submarine forces saturated the area. Destroyers, corvettes, and patrol craft equipped with the latest ASDIC technology watched for U-boats day and night. Aircraft flew constant patrols overhead. The channel had become a graveyard for submarines. Several U-boats had already been lost trying to operate in those deadly waters. But if the Albrick coating worked, if U-480 could truly evade detection, the channel offered rich hunting. Förster and his crew departed from Brest, France, on August 3rd. They had their orders: penetrate the channel, find targets, attack, survive. The first patrol was successful beyond anyone's expectations. On August 21st, U-480 encountered a Canadian corvette, HMCS Alberni, escorting a convoy about 25 nautical miles southeast of the Isle of Wight. Förster positioned his submarine carefully. He waited, watching through his periscope as the corvette passed nearby. The Alberni had ASDIC. She was actively searching for submarines. Her operators were sending out sonar pulses, listening for echoes. But they detected nothing. The Albrick coating was working. U-480 was invisible. Förster gave the order. His crew launched several Zonkönig acoustic torpedoes, weapons designed to home in on the sound of a ship's propellers. The torpedoes ran true. One struck the Alberni on her port side, directly behind the engine room. The explosion was catastrophic. The corvette's back broke. She sank in less than 30 seconds, taking 59 of her 90 crew members with her. U-480 slipped away undetected. It was a stunning success, but Förster wasn't finished. 3 days later, on August 24th, he struck again. This time the target was HMS Loyalty, a British minesweeper. Again, the Albrick coating allowed U-480 to approach undetected. Again, the torpedoes found their mark. The Loyalty went down. More Allied sailors lost their lives. The next day, August 25th, Förster attacked convoy BTC-78. He positioned U-480 on the convoy's expected route and waited. The convoy passed directly over him. The sound of propellers filled the submarine, a deafening thunder that vibrated through the steel hull. Forster counted the ships passing overhead. He waited for the perfect target. Then he saw it. The SS Orminster, a 5,000-ton freighter straggling behind the main convoy body. An easy target. He fired. The Orminster erupted in flame and smoke. She began settling by the stern. The convoy escorts immediately sprang into action. They had lost one of their charges. They knew a U-boat was nearby. 4 anti-submarine vessels began a systematic search of the area. 2 of them were equipped with ASTIC. They started sending out sonar pulses, searching methodically for the submarine they knew must be there. This was the moment of truth, not just for U-480, but for the Alberic technology itself. For 7 hours, Forster and his crew endured a terrifying ordeal. The Allied ships hunted them relentlessly. Sonar pulses pinged through the water, searching. U-480 sat silent at depth, trying not to make a sound. Every man aboard knew that a single mistake, a cough, a dropped tool, any noise at all, might give away their position. But the Alberic coating did its job. The sonar operators aboard the Allied vessels heard nothing. Or rather, they heard echoes, but weak ones, confused ones, echoes that didn't match the signature of a submarine. They dropped depth charges, hoping to get lucky. The explosions hammered U-480's hull. The lights flickered. Men gripped their stations, teeth clenched. But the charges fell hundreds of yards away, too far to do any real damage. After 7 hours, the Allied ships gave up and moved on. They couldn't find what they couldn't detect. U-480 had survived. More importantly, she had proved that Eric Meyer's rubber coating, dismissed as useless 4 years earlier, actually worked in combat conditions. But the story doesn't end there. In fact, in many ways, this was just the beginning. Chapter 6. The hunter becomes the hunted. News of U-480's success traveled quickly through German naval intelligence. Here was proof that the Alberic coating was effective. The reduction in sonar echo, combined with the sound-dampening properties of the rubber, made submarines significantly harder to detect. The Oberkommando der Marine, the German Navy High Command, immediately began planning to expand the program. The plan was ambitious. New Type 23 and Type 26 submarines, currently under development, would all receive the Alberic coating. Existing submarines would be retrofitted when they returned to port for maintenance. If enough submarines could be coated, if enough invisible hunters could be unleashed into the Atlantic, perhaps the tide of the submarine war could be turned. But there were problems, serious ones. The synthetic rubber required for the coating was in desperately short supply. Germany's industrial capacity was being hammered by Allied bombing. Raw materials were scarce, and the application process remained incredibly labor-intensive. Even with experienced crews working around the clock, it took weeks to properly coat a single submarine. Germany simply didn't have the time or resources to implement the program on a large scale. Still, they tried. About a dozen submarines received the Alberic coating in late 1944 and early 1945. Among them was U-LM-05, nicknamed the Black Panther because of her dark rubber skin. U-485 and U-486 also received the treatment. A Type 23 boat, U-4709, became the only submarine of that advanced class to be coated before the war ended. These submarines had mixed success. Some, like U-480, performed brilliantly. Others found the coating peeling off despite the improved adhesive. The problem was that every submarine hull was slightly different. Variations in construction, slight differences in steel composition, even the way the hull flexed under pressure, all of these factors affected how well the adhesive bonded. There was no one-size-fits-all solution. Meanwhile, Allied intelligence was growing increasingly worried. Reports filtered back from convoy escorts. Sonar operators were having unusual difficulty detecting U-boats. Submarines were appearing where they shouldn't be, attacking from positions where they should have been detected long before. Something had changed. By January 1944, British intelligence had received confirmed reports about the rubber coating experiments. Interrogations of captured U-boat crews yielded tantalizing hints about a special stealth technology. By November 1944, the British Admiral's Submarines forwarded a report to the Admiralty. The conclusion was clear. The Germans had developed a technical measure to defeat S-stick detection. The Allies needed to find out more about this technology, and fast. But fate intervened before the Allies could fully understand what they were facing. On January 6, 1945, U-480 left Trondheim, Norway, on her third patrol. Forster had been awarded the Knight's Cross for his previous successes. He and his crew were confident they had the best stealth technology available. They had experience. They had survived when so many other U-boats had been lost. They were the elite, the invisible hunters. They never came back. Exactly what happened remains unclear even today. What we know is that U-480 encountered a British minefield codenamed Brazier D2. This was a secret defensive minefield laid in the channel specifically to trap U-boats. Sometime between January 29th and February 20th, U-480 struck a mine. The explosion ripped open her stern. Water rushed in. The submarine plunged toward the bottom. All 48 crew members perished. The wreck lay undiscovered for over 50 years. In 1997, sport divers exploring the area southwest of the Isle of Wight found a submarine on the seabed at a depth of 180 feet. The following year, nautical archaeologist Innes McCartney correctly identified it as U-480. Remarkably, much of the alberic coating was still attached to the hull after more than 5 decades underwater, a testament to the improved adhesive that had finally solved the bonding problem. Chapter 7. The Allied Response. When Germany surrendered in May 1945, Allied forces rushed to capture German submarine technology before it could be taken or destroyed. They were particularly interested in 3 submarines, U-105, the Black Panther, U-485, and U-Olusex. All 3 had the alberic coating. All 3 had survived the war. U-115 became the prize. The British got their hands on her first. They conducted extensive tests, trying to understand how the coating worked. They measured the thickness of the rubber. They analyzed its composition. They tested how effectively it absorbed sonar pulses. The results astonished them. The German technology was more advanced than anything the Allies had developed. But the Soviets were also interested, very interested. At the Potsdam Conference, they insisted on inspecting U-1105. The British allowed it, but the submarine was heading for America. The U.S. Navy wanted to conduct its own detailed analysis. U-1105 crossed the Atlantic in December 1945, towed through winter storms that would have challenged a fully operational submarine. She arrived in the United States and was taken to the Naval Research Laboratory. For the next 4 years, American engineers and scientists examined every aspect of her design. They removed sections of the alberic coating and studied them in detail. They conducted acoustic tests. They tried to replicate the technology. The research was classified at the highest levels. The United States Navy understood that submarine stealth technology would be crucial in any future conflict. But here's the surprising part. Despite having access to all of Germany's research, despite capturing actual alberic-coated submarines, despite understanding exactly how the technology worked, neither the United States nor the Soviet Union immediately implemented it on their own submarines. Why not? Several reasons. First, both nations were transitioning to nuclear-powered submarines. The new nuclear boats were fundamentally different from diesel-electric submarines. They were larger, faster, and designed to remain submerged for months at a time. The coating technology would need to be completely redesigned for these new submarines. Second, both nations focused on other methods of noise reduction. Better propulsion systems, quieter machinery, improved hull designs. These seemed like more straightforward solutions than covering submarines in temperamental rubber coatings. Third, and perhaps most importantly, the adhesive problem persisted. Even with the improved German formulations, the coatings had a disturbing tendency to peel off during extended operations. For submarines designed to remain at sea for months, this was unacceptable. A partially detached coating could be worse than no coating at all. So the technology languished. The Alberic coatings and their principles were studied, documented, and filed away. Erich Meyer's revolutionary idea, proven effective in combat, seemed destined to become a historical curiosity. But technology has a way of resurrecting itself when the time is right. Chapter 8: The Soviet Advantage. The year was 1970. The Cold War was at its height. Soviet and American submarines played an endless game of cat and mouse in the world's oceans. Nuclear-powered submarines carrying ballistic missiles patrolled deep waters, ready to launch their devastating cargoes if war ever came. Attack submarines hunted each other, trying to track and shadow their opponents without being detected themselves. The Americans had a significant technological advantage. Their submarines were quieter, their sonar systems were more advanced. U.S. submarines could detect Soviet boats from much greater distances than Soviet submarines could detect American ones. This asymmetry troubled Soviet naval planners deeply. In any conflict, their submarine fleet would be at a severe disadvantage. Then Soviet engineers remembered the German research they had studied 25 years earlier, the Alberic coating concept. What if modern materials science could solve the adhesive problems that had plagued the German version? What if they could create rubber tiles that would stay attached through months of underwater operations? They began experimenting with new formulations. Modern synthetic rubbers were far superior to the Opinol used in World War II. New adhesives developed for space and aircraft applications promised much stronger bonds. Computer modeling could optimize the size and distribution of the acoustic voids. By the mid-1970s, Soviet submarines began appearing with rubber tile coatings. The first boats to receive them were Victor-class attack submarines. Western naval intelligence noticed immediately. Soviet submarines were becoming harder to detect. The acoustic signature that American sonar operators had learned to recognize was changing, becoming fainter. The tiles worked, not perfectly. Early versions still had problems with delamination. Submarines would return from patrol with patches of tiles missing. But when the tiles were in place, they made a dramatic difference. Estimates suggested that the acoustic signature of Soviet submarines had been reduced by 10 to 20 decibels. That's a reduction to somewhere between 10% and 1% of the original sound intensity. In submarine warfare, this was revolutionary. A submarine that had been detectable at 5 miles might now only be detectable at 1 mile. That gave Soviet crews precious extra minutes to react, to dive deeper, to deploy countermeasures, to escape. The technology matured through the 1970s and 1980s. Later, Soviet submarines like the Akula class received tiles that were about 100 millimeters thick. These weren't simple rubber sheets, they were sophisticated composite materials with multiple layers designed to absorb different frequencies of sound. Different sections of the submarine received different tile configurations, optimized for the specific acoustic characteristics of the machinery in that location. Western intelligence agencies were alarmed. The acoustic advantage that American submarines had enjoyed for decades was eroding. Soviet submarines were becoming true stealth platforms. Something had to be done. Chapter 9: America Catches Up. The United States Navy had been monitoring Soviet tile technology with growing concern. By the late 1970s, they could no longer ignore the problem. If Soviet submarines were becoming harder to detect, American submarines needed the same capability. The Navy initiated its own anechoic tile program. In 1980, the submarine USS Batfish became the first American submarine to receive what the Navy carefully called special hull treatment. The name was deliberately vague. The technology remained highly classified. Even the term anechoic tiles was considered sensitive information. The American approach built on 35 years of material science advancement. The tiles used synthetic polymers that were far more durable than World War II-era rubber. The adhesive system used multiple bonding agents, creating mechanical, chemical, and physical bonds with the submarine hull. The tiles were designed to withstand extreme temperature variations from near-freezing surface waters to warmer depths and back again without losing adhesion. The void structures inside the tiles were sophisticated. Computer modeling had optimized their size and distribution to absorb modern sonar frequencies, which operated at different ranges than the Aztec systems of World War II. Multiple layers within each tile targeted different frequency bands. The outer surface was designed to minimize hydrodynamic drag, allowing the submarine to maintain speed without sacrificing stealth. Through the 1980s and 1990s, anechoic tiles became standard equipment on American submarines. The improved 688 class attack submarines received them. The new Seawolf class submarines were designed from the start to use them. The Virginia class submarines, the latest generation of American attack submarines, have thousands of these tiles covering their hulls. But the technology still wasn't perfect. Even with modern materials, delamination remained a persistent problem. Submarines would return from deployment with sections of tiles missing. The rough edges of these gaps created turbulence and noise, partially defeating the purpose of the tiles. The problem was fundamental physics. As a submarine dove deeper, the hull contracted slightly under pressure. As it surfaced, the hull expanded. This constant flexing, combined with the mechanical stress of moving through water, gradually weakened even the best adhesive bonds. The Navy tried various solutions: better adhesives, mechanical fasteners, redesigned hull surfaces with features to help grip the tiles. Nothing completely solved the problem. Today's submarine crews simply accept that tile loss is a normal part of operations. Submarines go through regular maintenance periods where damaged or missing tiles are replaced. Despite these ongoing challenges, the tiles work. Modern submarines are dramatically quieter than their predecessors. The combination of anechoic tiles, improved propulsion systems, sound dampening internal machinery mounts, and carefully designed hull shapes has made contemporary submarines incredibly difficult to detect. A modern nuclear submarine operating quietly at depth is among the stealthiest machines ever created by humans, and it all started with Eric Meyer and his useless rubber coating. Chapter 10. The Legacy. Today, virtually every modern military submarine uses some form of anechoic coating. Russian submarines, American submarines, British submarines, Chinese submarines, French submarines. The technology that Eric Meyer developed in the late 1930s, that failed so spectacularly in 1941, that proved itself in combat in 1944, has become fundamental to submarine design. But the story doesn't end with submarines. The principles of acoustic absorption have found applications across military technology. Stealth aircraft use radar-absorbing materials based on similar concepts. Special operations boats and ships use coatings to reduce their acoustic signatures. Even some civilian applications, like noise barriers along highways or sound-dampening panels in buildings, use descendants of these technologies. The path from Meyer's laboratory to modern submarines wasn't straight or simple. It took years of failure, incremental improvements, and fundamental advances in materials science. Many talented engineers and scientists contributed, but the core insight, that carefully designed voids in rubber could trap and dissipate sound waves that came from Erich Meyer and his team in 1939. It's worth reflecting on what makes this story remarkable. A technology was developed, it failed, it was dismissed as useless. Years passed, then someone gave it another chance. Better materials solved old problems. The technology proved itself in combat. More years passed. The technology was forgotten. Then it was rediscovered. It was improved again, and again, and eventually it became indispensable. This pattern repeats throughout the history of technology. Ideas that seem impractical or useless in one era become essential in another. The difference between failure and success is often just persistence, the willingness to keep trying, to find better materials, to solve seemingly unsolvable problems. Erich Meyer didn't live to see his coating become standard equipment on submarines around the world. He died in obscurity after the war, his contribution largely forgotten. The Alberic project was classified for decades. Even today, many details about modern anechoic tiles remain secret. But Meyer's fundamental insight changed naval warfare forever. There's another lesson in this story. It's about the nature of technological advantage in warfare. The Alberic coating gave German U-boats a significant edge in 1944, but by then, the war was already lost. Germany simply didn't have the industrial capacity or resources to implement the technology widely enough to matter strategically. Even the best technology can't overcome fundamental deficits in production, logistics, or strategy. The same principle applies to modern military technology. Having the most advanced weapons doesn't guarantee victory if you can't produce them in sufficient numbers, maintain them properly, or employ them effectively. Technological advantage is important, but it's only one factor among many. Chapter 11. The Future of Stealth. Where does submarine stealth technology go from here? The fundamental challenge hasn't changed. Submarines need to avoid detection while operating in an environment where sound travels efficiently and where adversaries have increasingly sophisticated detection systems. Modern anti-submarine warfare uses multiple detection methods. Passive sonar listens for the sound submarines make. Active sonar sends out pulses to detect submarines acoustically. Magnetic anomaly detectors sense the distortion a submarine's steel hull creates in Earth's magnetic field. Radar can spot periscopes or communications masts. Infrared sensors can detect the heat signature of a snorkeling submarine. Satellite systems can potentially detect the wake a submarine leaves on the ocean surface. Anechoic tiles address only one part of this challenge. They reduce acoustic signature. But as detection technology improves, submarines need to become even quieter. Research continues into better acoustic materials. Some modern designs use active acoustic cancellation, similar to noise-canceling headphones, where sensors detect incoming sonar pulses and the submarine's hull vibrates in precisely calculated ways to produce destructive interference, canceling out the sonar echo. Other research focuses on making submarines smaller and more efficient. Unmanned underwater vehicles can conduct missions without risking human crews. These robotic submarines can be designed from the ground up for minimal acoustic signature. They don't need life support systems, crew quarters, or most of the machinery that makes conventional submarines noisy. Advanced materials research continues. Scientists are developing metamaterials, artificial structures with properties not found in nature that can bend sound waves in unusual ways. Imagine a coating that doesn't just absorb sonar pulses, but actually deflects them away, making a submarine appear to be somewhere it isn't. Such materials exist in laboratories. Whether they can be adapted for practical submarine use remains to be seen. The ocean environment itself presents another frontier. Different water layers have different temperatures and densities. Sound waves can bend or reflect at these boundaries. Submarines can potentially use these natural acoustic channels to hide or to confuse enemy sonar. Research into ocean acoustics, into understanding exactly how sound behaves in different marine environments, continues to advance. But here's the paradox. As submarines become quieter, the ocean becomes noisier. Increased shipping traffic fills the seas with acoustic clutter. Offshore energy platforms contribute to the noise. Even renewable energy, like offshore wind turbines, adds to the acoustic background. This noise pollution might actually benefit submarines, giving them more background sound to hide in. Or it might make detection easier, as advanced signal processing can filter out background noise to find the faint acoustic signature of a submarine. The future of submarine warfare will likely be a technological arms race. Better stealth technology versus better detection technology. Each advance in one drives advances in the other. It's a race that began with Eric Meyer's rubber coating and continues today in research laboratories around the world. Epilogue: the importance of failure. Let's return to where we started, the North Atlantic in 1941, U-67 limping back to port with her revolutionary coating peeling away. Engineers staring at the failure, wondering where they went wrong. At that moment, it would have been easy to give up. The technology clearly didn't work. The resources would be better spent elsewhere. Move on to something more promising. But someone didn't give up. Someone believed the idea was fundamentally sound and that the problems could be solved. That persistence, that refusal to accept failure as final, made all the difference. This is true across all fields of human endeavor, not just military technology. Many of our most important innovations went through periods of failure before achieving success. The Wright brothers crashed many times before achieving powered flight. Thomas Edison tested thousands of materials before finding a practical light bulb filament. Every successful technology has a history of failures behind it. The key is learning from failure. Understanding what went wrong, identifying the specific problems, finding solutions, testing again. The German engineers didn't just give up on the Albrecht coating, they analyzed why the adhesive failed. They worked on developing better bonding agents. They tested new approaches. When the improved adhesive was ready in 1944, they tried again, and it worked. This iterative process, this cycle of hypothesis, experiment, failure, analysis, and refinement, is fundamental to scientific and technological progress. It's how humanity advances. Every failure contains information. Every unsuccessful experiment teaches us something. The question is whether we're willing to learn from our mistakes and try again. Eric Meyer's story is ultimately about persistence in the face of failure, about believing in an idea even when everyone else thinks it's useless, about the long, frustrating process of turning a concept into working technology. It's about how innovation actually happens, not through sudden breakthroughs, but through years of incremental improvements, solving one problem at a time. The next time you hear about some promising technology that failed to live up to expectations, remember the Albrecht coating. Remember that what seems useless today might become essential tomorrow. Remember that the difference between failure and success is often just time, resources, and the willingness to keep trying. Conclusion: invisible guardians. Today, submarines patrol the world's oceans, largely invisible to detection. They carry nuclear weapons, serving as a deterrent against global conflict. They conduct intelligence gathering, monitoring potential adversaries. They protect sea lanes and project naval power. And their ability to do all of this depends, in part, on thousands of rubber tiles bonded to their hulls. These tiles, descendants of Eric Meyer's perforated rubber sheets, absorb sonar waves and dampen internal sounds. They turn submarines into acoustic ghosts, present but undetectable. They represent decades of research, failure, refinement, and improvement. They embody human ingenuity and persistence. The sailors aboard modern submarines might not know the full history of the technology that helps keep them safe. They might not know about U-480 and her combat success in the English Channel. They might not know about Erich Meyer and his acoustic laboratory in Germany. They might not know about the years of failures and the scientists who refused to give up, but they benefit from all of it. Every time a submarine dives below the waves and vanishes from detection, it demonstrates the legacy of that useless rubber coating from the Second World War. A technology dismissed as a failure, a gadget that almost ended up forgotten, an idea that changed naval warfare forever. This is how progress happens. Not through dramatic overnight breakthroughs, but through steady work, persistent effort, and the refusal to accept failure as final. Erich Meyer and his team gave us a glimpse of this process. They showed us that even ideas that seem useless can become revolutionary, given enough time and determination. The next time you hear about someone's useless invention, remember this story. Remember that today's failure might be tomorrow's breakthrough. Remember that the path from laboratory curiosity to world-changing technology is rarely straight or simple. And remember that some of the most important innovations came from people who refused to give up when everyone else said their idea was impossible. Somewhere beneath the ocean surface right now, submarines are moving silently through dark waters. Their crews are safe, in part, because of rubber coatings that absorb sound, coatings based on principles developed more than 80 years ago by a German acoustician who wouldn't accept failure. That's the real story of how one engineer's useless gadget made submarines invisible. It's not just a story about technology, it's a story about persistence, innovation, and the patient work of turning failure into success. It's a reminder that the difference between useless and revolutionary is often just time, effort, and the courage to keep trying. And that's a lesson worth remembering whether you're trying to change naval warfare or simply trying to solve the problems in your own life. Don't give up too soon. Don't accept failure as final. Keep working, keep improving, keep trying, because sometimes the ideas that seem most useless turn out to be the ones that change the world.